All right, so we're going to talk about proteins in this lecture. So in biology, there are 4 types of macromolecules: proteins, carbohydrates, lipids, and nucleic acids. Proteins are often referred to as molecular machines because they do things just like machines do things. So molecular machines, what do they do? One of their functions is to provide structure. They transport molecules. They speed up reactions. In this case, they're called enzymes. And they also are involved in muscle contraction, immune response, and tissue repair. Proteins are made of amino acids. So if you look at this example here, we have our protein robot, our molecular machine on the right, and then the components that we need to make that robot. So what I thought of was we need our fasteners, our bolts to put things, like connect things together. We need our electronic components. That's some sort of like raspberry or something. We need our iron ore, because that's how you make the metal, I'm pretty sure. I'm not really sure how metal is made outside of mining for the ore and then processing it. And then you need our paint. We need the paint. So we have our bucket of paint and all those things together, and we can make a robot. So if those components make the protein, those are amino acids. So this is what an amino acid looks like. We have a nitrogen on the left side called the amino group. We have the central carbon. Then we have a carbon with 2 oxygens, a carboxyl group on the right, and then on the bottom is the R group, that multicolored R group, just showing that it can vary. That's the part that can change, but everything else is the same for all amino acids. So here we go. Yeah, we have the amine group on the left. That's basic. Basic means it accepts hydrogens. We have the hydrogen group, we have our central carbon, and then we have the carboxyl group, which is acidic, so it'll donate hydrogens. There are no hydrogens there right now, but that's just because it had already donated hydrogen. So that's like after it had donated the hydrogen. And then lastly, we have the R group, which varies depending on the amino acid. So the top 3 parts, those are always there on every amino acid, but the R group is the thing that can change. So amino acids can join together by peptide bonds. So when they connect with each other, they link up. That's called a peptide bond. So here we have 2 amino acids right next to each other. The 2 hydrogens on the amino group of one amino acid will give their hydrogens over to the carboxyl group of a nearby amino acid. So it gives those hydrogens over to the oxygen, and now that oxygen becomes water. It's H2O. H2O doesn't like to stay on a molecule. Like if you see how water, that's H2O and it's connected to a molecule. H2O doesn't want to connect the molecule. So once it gets formed like that, it's going to break off the molecule. Basically, usually this is all happening in water, like because our bodies are mostly water. So it's going to leave and just become the rest of the water. It's going to leave and it's just going to join the rest of the water in the body. So it's going to be water. On the left, the water has left now. So now that carbon is there, and it's positive because that water is electronegative, the oxygen is, so it's going to steal all the electrons with it. So now that carbon doesn't have many electrons left. It wants electrons. But now we have a nitrogen on the right, which when hydrogen leaves nitrogen is not very electronegative, so it's not going to take any electrons with it. So now this nitrogen's got a whole bunch of electrons. It doesn't want all those electrons. The carbon on the left wants electrons, so now that nitrogen will give some of its electrons over to that carbon in the form of a bond. Like that. So nitrogen is giving some of its electrons to carbon. They're sharing the electrons, and this forms a covalent bond. A covalent bond is formed. So multiple amino acids can do this in a row. Like a whole bunch of them can do this, and they link up and form these long chains called polypeptides with peptide bonds between each amino acid. So as you can see here, all those are peptide bonds. And when this polypeptide chain, they link up and it's 100 amino acids, at least 100 amino acids are linked together, that's called a protein. So here are all the types of amino acids. There's 20 of them. There are more than that, but though after these 20, the rest of them, you don't really see them very often. These are the main ones. So there's 20 of them, and they're separated by group. So some of them are non-polar, some of them are polar, which basically means the non-polar ones don't dissolve in water, but the polar ones do dissolve in water. And then we have ones that are, that positive and negative charge just means, so the positive charge means basic. Those are ones that will give hydrogens, and the negative charge are ones that are acidic. They will donate hydrogens. Okay, so if we look at a peptide chain again, and then we have those little markings in between just to show like where one amino acid begins and the other one separates, right? That marking is where a peptide bond is. Now, let's say that each one of the amino acids will substitute in the R group. So let's say that, yeah, we put in our R groups. So now we have methionine, alanine, histidine, threonine, and aspartic acid as our amino acid chain. The type and order, so this, like how you can see, this is the type, each type of amino acid, and the order, that's called the primary structure. Okay, so this polypeptide chain, that's part of a bigger protein. So on the right is a protein, that noodle thingy, let's say that's a protein, and it's made of amino acids all linked together. So that's all this is showing. Now, this protein can coil onto itself, like as shown on the right. That's called an alpha helix when it does this. What's happening in the alpha helix, what's holding it in this shape, is hydrogen bonds. So if you can imagine, we have a polypeptide chain, and now it stacks on top of each other like this, or coils around. And then these hydrogen bonds between oxygen and hydrogen are what holds it into this coiled shape. So hydrogen bonding between oxygen and hydrogen causes the amino acid chain to coil onto itself. So the protein can either become an alpha helix or a beta pleated sheet on the right. So these are just two different structures the protein might go into, right? It can do this sort of zigzag formation, or it can do the helix. So for the beta pleated sheet, this is really similar. It's the same thing that holds it together, but just it just, for whatever reason, forms a different shape. Instead of doing the helix, it does like this zigzag thing. But it's the same scenario, right? It's hydrogen bonding between an oxygen and a hydrogen of the amino acid above it or below it. And that's what holds it in this shape. So when the protein either becomes an alpha helix or a beta pleated sheet, that's called the secondary structure of the protein. So alpha helices and beta pleated sheets are secondary structures. So let's say we have a protein that looks like this. We have our protein, one part of it becomes the beta pleated sheet, another part becomes alpha helix, so those are the secondary structures. But this is when the protein is not done, right? After it does the secondary structures, it has one more thing it can do. So this is when we have to talk about the hydrophobic and hydrophilic amino acids. This is also what was called polar and nonpolar. So in this case, these would be the nonpolar amino acids. Hydrophobic means water-fearing. It means that it will not associate with water. So the hydrophobic amino acids are alanine, cysteine, isoleucine, leucine, methionine, glycine, phenylalanine, proline, tryptophan, and valine. I'm pretty sure there's a good acronym or mnemonic device you could put together to help memorize these, but I don't know of one myself. I don't know of any. Okay, so those are your hydrophobic amino acids. Then we have the hydrophilic amino acids. Hydrophilic means, and there's a mistake there. That's supposed to be hydrophilic, not hydrophobic. Hydrophilic means water-loving. So these are molecules that will associate with water, want to associate with water. So the hydrophilic amino acids are serine, threonine, tyrosine, asparagine, and glutamine. Okay, so Proteins usually exist in a water-based environment. So that means that they're just usually surrounded by water. Now let's look at this scenario. So we have our same protein, but let's say that we have these amino acids that are hydrophilic on the left and right, and then this hydrophobic amino acid that's in the middle, right? Because the proteins are made of amino acids. So let's just say that in the middle there's this tail that's just like sitting there, it's hydrophobic. On the outside are hydrophilic amino acids. The question is, how will this react? How will this protein change if those things are there? Well, it will fold onto itself like this so that the hydrophilic amino acids are exposed to the water and the hydrophobic amino acid is shielded, right? It's going to basically crumple around the hydrophobic amino acid because the hydrophobic amino acid doesn't want to be around water. So the protein is going to protect the hydrophobic amino acid. The hydrophilic ones do want to be with water, so those ones are going to stay exposed. This is called protein folding, and when the protein does this, right, when it tries to protect the hydrophobic amino acids and expose the hydrophilic amino acids, that's called the tertiary structure.